Okay, so at this point, we know already that Legendre polynomials basically are of two types, right? So I mean, we could have even Legendre polynomials. So Pn of x would be of the form a naught a2x squared plus dot 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 an x to the n if n is even, right? If you have an even degree, or you have it of the form a1x plus a3x third dot 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 anx to the n if n is odd. Now, that's not really that practical, so it's better to have a more closed format, and also it's better to have actually an explicit value for the coefficients. Now remember, because of that recursion, we can express a2, a3, and so on in terms of a naught, if you keep on plugging in what you have in that recursion. But that's not practical to do all the time, and again, that doesn't specify how you should choose a naught and a1. And the way to choose this is basically for practical purposes. As we move along with the material, you will notice that certain operations happen more often with these Legendre polynomials. So some of the values of these polynomials at different points are essentially equal to a certain number out of convenience. In other words, the choice of these coefficients, the starting coefficients, is in such a way that the polynomials have more practical properties. And so one of them, which we should specify right now, is that a naught or a1 is chosen such that Pn of x, Pn of 1, sorry, is equal to 1 for every n. Doesn't matter if it's odd or even. Okay, so all Legendre polynomials go through the point 1, 1. So that's the first thing to keep in mind. And again, why that's practical, you'll see later. I might remind you again that the typical domain in our problems is -1 to 1, right? The maximum domain that ends up in if you have a sphere. So I mean, you know, you have often the opportunity to plug in 1 for this for x in these Legendre polynomials. And so for practical purposes, that is basically a desirable property. Once we impose that you want these polynomials to have this condition, that will force essentially the coefficients to have a specific value. It's not going to be pretty, it's not like a nice, easy value, but they will have a specific value that you can show. We're not going to go through all the details in this class, but you can show that those values must be in that format if you want this property. So one of them, I'm going to just give these as they are in the formula sheet. an is going to be 2n factorial over 2 to the n factorial to the power 2. And the choice for a naught is going to be -1 to the n over 2, 1, 3, all the way up to n minus 1 divided by 2, 4, 6, up to n, if n is even, that is 2, 4, 6, and so on. And the starting value in the odd case is -1 to the n minus 1 over 2, and now on the top you have 1, 3, 1 times 2 times 3 up to n divided by 2, 4, 6 up to n minus 1. That is if n is odd. So if n is 1, 3, 5, and so on. These will be homework problems. You have 3 homework problems so far, and the first homework on the Legendre polynomials. So starting with the formula for the general polynomial, which I'm going to illustrate right now, you can show that given this choice of an, that implies the starting value of a naught and a1 to be on this form. I know this seems like kind of strange, but again, it's all because you want essentially these polynomials to have certain properties, one of them including this value, 1x is equal to 1. Fortunately, just like in the case of Bessel functions, we won't need to play with these coefficients explicitly. We're going to have computation rules involving Legendre polynomials, but for a while in the beginning, we have some practice exercises to just use directly the formula for these polynomials and play with these coefficients just for practice in the beginning. So the next thing I want to talk about, because I still didn't mention, was the general format. So how do you write Pn of x for any n? So there is actually such a closed format. So the general form of a Legendre polynomial, again, is not going to be a pretty formula, but at least it's in one setting, essentially. So this encapsulates both types, even or odd. So it's 1 over 2 to the n, summation from 0 to m, and I'll say immediately what m is, minus 1 to the k over k factorial to n minus 2k factorial over n minus 2k factorial, n minus k factorial, and x to the n minus 2k. There's another one way to derive these coefficients via a formula called Rodriguez formula, but I'm not going to talk about that. It's a more compact form, though, that involves taking repeated derivatives. It's just more compact on paper. So what is m? So where m is equal to n over 2 if n is even, and n minus 1 over 2 if n is odd. Okay, so although this looks like a fraction, this is, both of these are natural numbers, right? Because if n is even, then this will be a natural number. If n is odd, n minus 1 odd, this will be even. So when you divide by 2, you end up with a natural number. So this allows you to write this in a compact form. Notice that in the even case, when you start with what I was going to say, when n is even, when you have k equals n over 2, that's x to the 0, right? So that'll be basically the first term, a naught, right? And if k is equal to n minus 1 over 2, when n is odd, when you plug in n minus 1 over 2 here, you get x to the power first, which is obviously the first term in the even in the odd case. Let's say someone asks you to actually come up with an explicit format for the polynomial for various values of n, right? So let's say someone says, okay, tell me what is exactly p2 of x, what is p5 of x, right? So it's just a matter of plugging in all of these terms here. So when n is 2, the summation goes up to 1, right? Because m is 2 over 2, which is 1. So if n equals 2, it's going to be 1 over 2 to the power 2, the summation from 0 to 1, minus 1 to the k factorial. 2 times 2 becomes 4 minus 2k factorial. 2 minus 2k factorial, 2 minus k factorial, x to the 2 minus 2k. This looks kind of ugly, but there are only 2 terms if you look carefully, right? So I mean, first when you plug in 0 for k, so that's minus 1 to the 0 over 0 factorial, that's 1. Then 4 minus 0, that's 4 factorial on the top, 2 factorial on the bottom, another 2 factorial, and then when k is equal to 0, as I said already, x squared. And then the next term, 1 over 2 squared. Now k is equal to 1. There's another term in the summation, so minus 1 to the first is minus 1 over 1 factorial. That's a minus 1. 4 minus 2 factorial, that makes it 2 factorial. On the bottom here, when k is equal to 1, that makes it 0 factorial, which is 1. And 2 minus 1 factorial, which is another 1. And now the power of x, if k is equal to 1, that's x to the 0, which is just a constant. So let me see if I can squeeze it here. I want to simplify it a little bit. 4 factorial, that's, let me do it separately just a second. 1 times 2 times 1, 2, 3, 4 divided by 4 and times another 4. That's 3 over 2. So that's 3 over 2x squared. And let's see, this is 2 factorial, which is 2 over 4. That's minus 1/2. Minus 1/2. So 3 over 2x squared minus 1/2 will be the Legendre polynomial of degree 2. In fact, I was looking at the book right now. You have basically some example on page 331. So take a look at page 331 in the book for other examples, just to practice with the summation. And you have also the graph of some of them. Okay, let's do another example. P5 of x. Now, pay attention here, the summation goes up to n minus 1 over 2. N is 5, 5 minus 1 is 4, 4 over 3 is 2. Okay, so the summation goes from 0 to 2. We have 3 terms. So 1 over 2 to the power 5. Summation from 0 to 2 minus 1 to the k factorial. And now n is 5, right? So it's going to be 10 minus 2k factorial over 5 minus 2k factorial and 5 minus k factorial. All right, so I'm going to just let you simplify. Later on, I'm going to just expand the summation. So 1 over 2 to the 5th. And minus 1 to the 0 is 0, 0 factorial. So that's going to be 1. Oh, I forgot x, right? So this is multiplied by x to the power 5 minus 2k. It's kind of squeezed there, but, you know, 5 minus 2k over here. All right, so k equals 0 first. 10 factorial, 5 factorial, another 5 factorial, x to the 5th. Next one will be minus 1 to the 1st over 1 factorial. So it's going to be a minus 1. And that's going to be 10 minus 2 factorial. That makes it 8. 5 minus 2, 3 factorial. 5 minus 1, 4 factorial. And x to the power 3. Moving along, if k is equal to 2, minus 1 squared is 1. So we're going to have 1 over 2 factorial. This guy becomes 10 minus 4, 6 factorial. 5 minus 4, that's 1 factorial. 5 minus 2, 3 factorial. And then x 5 minus 4, which is 1. Okay, so do these simplifications on your own, these factorials. You should end up with 63 over 8 when everything is said and done, x to the 5th, minus 70 over 8, x to the power 3, and then plus 15 over 8x. Okay, so check to see that this together with, don't forget this 1 over 2/5 on the outside, but when you simplify all of these coefficients, you should end up with these coefficients here for the 5th degree Legendre polynomial. I want to finish with a couple of hints for the homework, but again, let me say one more thing so that you don't get discouraged. The good news is that we don't work with these ugly coefficients explicitly. We have rules that bypass this stuff, basically. So we have computation rules that bypass the need to do that. But remember, in life, you keep on writing P4 of x, P5 of x, and so on, but if someone says, okay, what is exactly that equal to, then you should refer back to this formula, and you should produce what that polynomial is term by term, if needed. In practice, we will be perfectly happy to keep the polynomials in that form, assuming we know what they stand for, just like in the case of Bessel functions. As a matter of fact, in the case of Bessel functions, it's even worse, because remember, those roots, alpha j's, were not in closed form, so we didn't know what they are. We only knew that they exist. So the homework, there are 3 problems in the homework, like I said, to play around with these coefficients. So some applications, one of them is how to obtain these A0 and A1. I want to give just a hint that is going to be needed for that, for some of those problems. Just a hint on the homework related to the factorials, when you simplify factorials. Some of these hints, by the way, are given in the problem itself. But one way to simplify factorials, so for example, suppose, for instance, that you have, let's say you have n factorial on the top, and on the bottom, let's see if that's what I wanted to say. Yeah, I mean, there are, so let me put it this way. Let's say you have basically factorial that involves just even numbers. So let's say you have 2, 4, 6, up to 2n. Okay, so basically a product of just even numbers. You can actually, just for purposes of simplifying, maybe with something on the bottom of a fraction, because that's what happens in those problems, it might be beneficial to pull all the 2's that come as factors of these coefficients, of these factors, right? So for example, because all of these are evens, you can pull up a 2 out of each factor. So you can think of 2 as 2 times 1. You can think of 4 as 2 times 2. You can think of 6 as 2 times 3, and so on. And so then, obviously, you can pull the 2 out of each factor. Now, the question is how many of them are. Now, notice that because you have 2 times 1 times 2 times 3 up to n, that tells you these are n factors. So you have to make sure that you count them carefully, right? That means you pull n factors of 2, and if you do that, you can write it as 2 to the n, and you're left with 1, 2, 3, n, which furthermore you can write it in a more compact form as n factorial. Now, this is when I explicitly said that the last term is 2n. Now, let's say, for instance, that I know n is even, and again, I have the same trick, right? I want to pull 2 out of each of these factors. I can do the same thing as before, and knowing that n is even, it's perfectly fine to write it as 2 times n over 2, because n over 2 again signifies a natural number, right? I mean, there's n over 2 terms if n itself is even, so therefore you pull out 2 n over 2 times, which means 2 to the power n over 2, and you're left with n over 2 factorial. So you will encounter often these types of quantities which you may think that they don't make sense unless they're natural numbers, but they will always specify that this is so if n is even, or in some other cases, you will have quantities like this if n is odd. So in all cases, you'll end up with natural numbers under the factorial, depending on whether n is even or odd, only divided by 2. So give that a try. If you couldn't make it through with those problems, just make sure you ask them during our live office hour. So that's it for today.